Hello everyone, welcome to the webinar. My name is Clarisse. I work here at iBwave in marketing and I will be your host for today. So today's webinar is on the evolution of private enterprise networks. And I'm joined by our guest speaker, Dean Bubley, and our senior research director, Vladan Jevremovic, for a deep dive into an industrial plant use case. So make yourself comfortable and feel free to ask any questions by using the GoToWebinar question box. We'll try to answer as many as possible at the end of our session. So also be aware that the webinar will be recorded and sent to everyone after the presentation. So now I'm going to hand the microphone off to Dean. Hello, Dean. Thanks for being with us today.
Hi, Clarisse. Thanks. Hi there, and thanks for listening into this webinar. I'm going to kick off for about maybe 20 or 25 minutes to talk about what I'm seeing with private networks for enterprise and also this term semi-private, and I'll explain what that means as I go through. So just as a quick introduction for people who don't know me, I'm an industry analyst and advisor. I tweet under the name of Disruptive Dean, which should give you an idea that I tend to be quite contrarian. I've actually been following private cellular networks since around about 2001 was the first time I saw a small cell and started discussing this. But really in the last 3 years, we've seen a lot of interest in private 4G and now private 5G networks coming partly catalyzed by CBRS in the US, but also developments elsewhere around the world. And I'll touch on some of those as I go through. So I look at network infrastructure, I look at service provider business models. I also do some stuff that looks at sort of wireless voice and video and other forms of personal communication, as well as use cases such as IoT and where it intersects with artificial intelligence and other future trends. But today I'm going to focus more on 5G, Wi-Fi, and a really important distinction, and saying that there's changes to both demand and supply for wireless networks at the moment in enterprise. There's ever more use cases and applications, and they're becoming ever more important for a whole host of reasons. And it's also likely to change a little bit because of the pandemic, and I'll touch on that later as well. But I think that the emphasis for today is probably more on the supply side, and that we're going from a world where there were only certain ways in which organizations could obtain connectivity on site and in their premises to ones where there's a lot greater choice and sophistication, both to internally develop connectivity and from different classes of service provider. So to sort of step back a bit, there's sort of two dimensions to look about wireless, particularly indoors or on site, and you can divide it between private networks and public services. And I'll make the distinction where a private network is infrastructure which is owned by an organization itself, similar to the fixed LAN environment and Ethernet and so on. And then public services are those delivered typically by a telecom operator or MNO, mobile network operator, and often they relate to the provision of macro network services on-premise, on-site, in buildings, whether that's for visitors, for employees, and perhaps I will talk about IoT later on. And so really you've had those split between unlicensed spectrum and licensed spectrum. Pretty much the unlicensed spectrum has been for private networks for Wi-Fi and a bit of public Wi-Fi for hotspots as well. And then the cellular infrastructure has largely been in licensed spectrum, typically licensed exclusively on a national basis in most countries, or at least regional in some others like say US or India. And then there's been a few niche examples of private networks using licensed spectrum, either for specialized use cases like utility grid control or perhaps broadcast usage, which might be permanent or might be temporary, for example, outside broadcast at a sports event or something like that. But we've had this fairly good split between private unlicensed and public licensed, and that is something which is now changing. It's been changing over time in a number of ways already, but this is really now going to hit an inflection point in the next couple of years. And there's an important issue here, and that's around demarcation points. For most of the utilities or other services we have coming into a building, there's a very clear separation point between inside and outside, where there's a single point where for power or for water or for fixed broadband, on one side of it, it's the service provider's responsibility, and on the other side of it, it's the owner of the property that is responsible. And for wireless, that's not quite the case, because obviously you have wireless signals that go through the walls of buildings, and so you have both the outdoor service environment penetrating indoors, and the indoor, typically Wi-Fi, but increasingly also private cellular, leaking outdoors as well. And so this makes the sort of design and planning of that hybrid environment much more complicated. One of the challenges that we're going to have as we go into the 5G era, and also Wi-Fi 6, which I'll talk about, is the range, and especially the higher frequencies and frequency choices that are going to become important. And so whilst a lot of people initially thought of 5G as purely going to be using millimeter wave spectrum, what's actually happening in most of the world now is that mid-band 5G is becoming more and more important. In Europe, it's typically between 3.4 and 3.8 gigahertz. In the US and other markets, it varies by service provider. So say 2.5 gigahertz for Sprint in the US. You've got the C-band auctions coming out towards the end of this year as well, which may bring new ones. And also in some parts of Asia, it's in the 4 to 5 gigahertz range. And then you also have low band 5G. Not every service provider has this yet, but eventually most will. And that's low capacity, but that should have good indoor penetration. The issue is going to be whether that capacity is enough for various of the high-end services and capabilities we hope to get from 5G. And there is this paradox that the higher the bandwidth, the higher the frequency, that's where a lot of the what I call cool new stuff from 5G comes on, but it's also the frequency bands that work least well through walls and will need dedicated in-building systems of one form or another. And that gets especially complicated if you have an environment that needs coverage from multiple different network operators. We also have some changes going on with spectrum for Wi-Fi. We have existing 2.4 and 5 gigahertz bands, but there's also, and especially in the US, a new large slice of unlicensed spectrum in the 6 gigahertz range, which has just been announced by the FCC, and we should start seeing devices arrive maybe towards the end of this year, early part of next year. And that allows us to have 80 gigahertz or 160 gigahertz channels. It's going to be a huge addition to the Wi-Fi arsenal. In theory, we'll also see some 5G unlicensed running in that spectrum, but I suspect it's probably going to be a fair bit behind in terms of time before that gets to market. And that's again going to pose some both opportunities and challenges, given it's at a higher frequency than we're used to. Now, 5G, and we'll be hearing a lot more from Vladan about private 5G. Before we talk about private cellular, it's worth recognizing that 5G is not a monolith, and there will be multiple different phases of 5G over the next 3, 5, 7 years. And that's important because the first phase, which we have today, pretty much is just an upgraded version of 4G. It's designed primarily for mobile broadband for smartphones and also for fixed wireless access primarily. And although there's some early IoT use cases for display screens or cameras and so on, it's predominantly been aimed at the consumer market for now. That changes pretty much starting, well, now or over the next 6 months, with the beginning of what I'll call here phase 2, but people listening in will probably recognize the term of release 16 of the 3GPP standards. And release 16 and then release 17 and finally 18 will have progressively more enterprise-grade features, both for service providers, but also for private networks, or as the 3GPP calls them, non-public networks, rather confusingly. And some of the capabilities there involve what's called the standalone core network, whereas today's actually relies on the 4G core. From now onwards, we'll start seeing 5G networks that have their own new core network, which allows for things like network slicing, and it's essentially more scalable and also based on microservices, cloud native architecture for the 5G new core, which ultimately is one of the key enablers of a lot of the other advanced features that we hope to see in coming years. And then over time, we start getting additional things built into subsequent parts of like phase 3 of 5G. So what's called ultra reliable low latency communications, time sensitive networking, which is deterministic timing for, say, industrial use cases, a number of vertical specific features for different sectors. And we can expect all of those to appear in phases over the next few years. On the private network side, the red chevrons at the bottom of this slide, it's worth pointing out that today, most private cellular is 4G. Particularly CBRS networks in North America are LTE. Based. Now that's starting to change, and we're starting to see the very earliest private 5G networks initially as trials and test beds, but probably from mid to late next year, more mainstream deployments of private 5G in a variety of environments. I'm already seeing them in, say, some of the German deployments for industrial uses. We'll see them perhaps in North America, Japan, UK, and a number of other markets. But it's going to take a little while before the full value chain of systems integrators, specialist suppliers, and indeed the internal skill sets within most organizations are built up to the point of where they actually become more viable for mainstream mission critical deployment. At the moment, it's still mostly trial use. So what we've got is on the left, there's this sort of licensed versus unlicensed, private versus public split that I was talking about before. What's happening now is that's changing into a rather more complicated landscape where on the bottom, as well as the traditional unlicensed and exclusive licensed spectrum, there's this new category I've put in the middle of local and shared spectrum. And there's a variety of different models for this, where you can either, as an enterprise, apply for spectrum for a specific site or building in some countries. In others, there's a more dynamic and database-driven approach to, can I use this part of the spectrum at this time in this place with this power? And that's probably more, the latter is more true of CBRS, for example, in the US, whereas other markets in Germany, for example, where you essentially have a geo-fenced license for a particular band on essentially a first come first served basis. So spectrum policy is really changing. I'll talk a little bit more about that later, but that's something to keep an eye on in your particular market. And as I say, in North America, it's more driven by a database and dynamic approach. CBRS uses a feature called the SAS, the Spectrum Access Services, and there's a number of companies which essentially allow you to work out if you're allowed to use that particular band of 3.5 gigahertz at a particular time in a particular place. So on the vertical access, we've gone from having private wireless networks like Wi-Fi and public operators like cellular providers or public hotspot managed service providers to this third category in the middle, and I'll call them specialist wireless services, or you could call them semi-private networks. And this is a little bit of a nuanced grouping, but essentially it's where a non-telco, let's say an industrial equipment supplier or a specialized service provider that just focuses on IoT or just focuses on the oil and gas industry or manufacturing or public sector or private and maybe healthcare or something like that, act as a mobile network operator or a Wi-Fi or a hybrid operator for particular classes of business and particular types of organization. And it's a little complicated, but for example, if you're an airline, a good example here is in Germany, where Lufthansa has now a couple of private network trials that it's doing, and in one case it's using a purely private network which is built in one of its hangars, and in another it's working with, in fact this case actually Vodafone in Germany, but not as part of their public network, but offering a localized dedicated network that's just been used using the service provider as an engineering resource and potentially management and maintenance. And I think we're going to have probably a couple of years of fragmentation of business model here. It's going to be very verticalized. It's going to vary by country. You'll see a lot of people who have backgrounds in IT, in OT, which is operational technology, maybe coming from a critical communications background where they've provided push to talk in the past for particular verticals. I think it's going to be a really vibrant space, and there's a lot of interesting companies that either have got their own spectrum, or they will work with lease spectrum from a carrier, or where the enterprise itself has gone out and got spectrum. And this sort of ties in with the demand side of this. And here, the red classes of device and user are the traditional users of enterprise connectivity. And there's obviously more as well, but I've highlighted these as being the most important. And often it's employees and sometimes visitors' smartphones, and also PCs and tablets, and then a few handhelds for things like payment terminals in retail, or maybe barcode scanners in a warehouse, as well as on-premise vehicles in certain instances. What is happening now, and this ties in with a much broader trend towards transformation of business processes, automation, particularly in industrial sectors, but also in everything from healthcare to government and retail, is you're seeing a lot more connected devices, and they're typically connected and mobile, or at least wireless connected. So we're seeing ever more cameras and displays of different sorts, industrial automation, and you'll hear more about that from Vladan, sensors most obviously in everything from manufacturing, but also smart buildings, even agricultural, indoor farming, for example, things you don't necessarily expect straight away. There's a lot of interesting industry groups here that are really specializing in real-time, what's called closed loop automation, where data is captured from sensors, processed, and then some other process occurs automatically without necessarily human intervention and oversight. And it could be for maintenance, for particularly preventative maintenance. Imagine, for example, you have a machine which is vibrating or has a temperature which is unusual and anomalous, and it's temporarily shut down pending an inspection to avoid a catastrophic failure at a later point. So there's a lot of other classes here, everything from AR and VR gets widely discussed, moving vehicles, and AGVs are automatic guided vehicles. So think of an autonomous forklift truck. It might be portable equipment in a hospital with an asset tag, tracking tag, when it's wheeled around from different wards or between different buildings. So I think that one of the things that enterprises are going to have to do is think through not just who is using their wireless infrastructure, but what are the device classes that are likely to be attached, because that will help determine the applications, their connectivity types, whether cellular is appropriate, for example, if you have to go outdoors as well as indoors on a campus environment like a port or an airport. And I think that this sort of nice, fairly easy binary of unlicensed Wi-Fi versus licensed cellular is going to have to break down, and we're going to have to give a lot more thought. So one of the trends that's definitely changed, compared to if I'd been giving this presentation a year ago, is the number of different spectrum bands available for private cellular use. And CBRS in the US, is probably a lot of people on this call from North America, is between 3.5 and 3.7 gigahertz. But around the world, there's a variety of different approaches, both in terms of the frequency band and in terms of the allocation mechanisms, pricing, and other ways and rules on power and trading of secondary license marketplaces for secondary trading of spectrum held by existing service providers. One pattern I would say that's starting to emerge is this sort of mid-band, typically between 3.4 and 4.2. In a lot of countries, there will be some of that available for private 4G and especially 5G. So UK has got 3.8 to 4.2. Germany, there's 100 megahertz, so between 3.7 and 3.8. Sweden may well follow that. I think the Czech Republic has about 40 megahertz that it's going to give in the same range, and so on. The other trend that is happening, starting just to kick off, is millimeter wave, 26, 28 gigahertz, that's available on a local license basis, sometimes indoor only. And so certainly Japan, Malaysia, UK, possibly Germany are looking at that, and that will clearly be a 5G only band. In some countries, there's also some low band spectrum becoming available, particularly suitable for wide area private cellular networks, perhaps say for utility companies or rail or energy and oil and gas. In some cases, it's as low as 450 megahertz, going up to 700, 900. But this is a very, very dynamic situation. It's also been somewhat impacted by the pandemic. In some countries, there's been an acceleration, and in some cases, been a temporary halt to issuing of these licenses. But hopefully, in a few months' time, it should all settle down again. So, what are the if you like winners and losers here? Well, this chart, and you'll get a chance to download it, so I'm not going to go through every square on it on this call. What I'm seeing is a sort of a fair patchwork of different approaches, what is relevant for different use cases, whether that is in-building cellular for visitors, whether it's for industrial use cases, for verticals like public safety or utilities. I think that what you'll see is that increasingly local and shared spectrum will be used in industrial sites first, but also over time, perhaps on more visitor-centric venues like hotels or maybe airports, maybe sports venues, although obviously entertainment industry is not doing especially well at the moment. I think that Wi-Fi, and I'll flip onto a similar slide in a moment, Wi-Fi will remain exceptionally important for what I call general IT purposes. And that's particularly connectivity for laptops, for audio-visual devices like screens, which typically don't have cellular radios in any way. If you have things like voice assistants, and there's some, I think it's about 13 or 14 billion existing Wi-Fi only devices around the world. So there's often this discussion of Wi-Fi versus public or private 4G and 5G. I think it's a false binary. Now I'll talk a little bit more about that now. So I see Wi-Fi in particular retaining control in the residential space, which is not really relevant for this call, but is important for Wi-Fi generally. I think in carpeted offices, Wi-Fi will retain primacy, again, primarily because of things like laptop usage, and that's not just employees, but it could be visitors, consultants, auditors. The chances of anyone coming on site all of them having cellular only laptops is essentially zero. I don't buy the arguments that every laptop will be cellular equipped anytime soon, if ever. I think the variable here is in public spaces. I'm a big fan of easy log on for public Wi-Fi. I think that where you have complicated social logins and so on with poor privacy experiences, I think that's not helpful. And I think that's especially the case as 5G becomes more prevalent among the general population. But also I think that we're going to see some markets, notably industrial, where private or perhaps public semi-private 5G networks become much more prevalent. And although Wi-Fi or even industrial wireless LAN with proprietary tweaks will retain importance, I think that we're going to see over the next 4 to 5 years a growing role of private cellular in particularly industrial automation. It seems to have been very much grasped by that community, although it has to be said Wi-Fi 6 and 6E with 6 gigahertz also allows 2 milliseconds latency, and perhaps will recapture some of the ground there, especially if it's tailored to specific sectors in future. So one thing to say, you'll hear more about this from Vladan. 5G networks, and particularly private 5G, is not easy, and it's not for everyone. There's an awful lot of moving parts to build a cellular network, and just because it's a private cellular network for a smaller campus basis, for example, doesn't make it any easier. In particular, understanding things like the core network and what it does, how you deal with eSIM or SIM cards for authentication, whether you need to consider things like numbering and roaming. if you have devices that work both on-premise and off-premise. And then if, in some cases, if you're using it for things like walkie-talkie replacement, for two-way radio replacement, you have to start thinking about how you deliver voice capabilities or messaging on something. And that's non-trivial if you have to start looking at getting either a private IMS or something similar. Now, one thing I will say is that although there's a lot of components for cellular networks, these are getting both easier and more cloud delivered. I speak to any number of companies that are trying to do core network or SIM management as a cloud delivered service. And I think we'll see that become increasingly sophisticated over the next 12 to 18 months. So just a sort of final sort of chart comparing Wi-Fi against private cellular and public. This slide will be in the deck, so you can see it in more detail at your leisure. I think that for indoor coverage of ordinary cellular, whilst there is a bit of offload to Wi-Fi, I think that in continued development of public networks using small cells and DAS will continue. And I think that there's another side we haven't talked about here today called neutral host, where a third party offers a cellular network run on a wholesale basis with essentially local roaming deals for indoor coverage. And that's becoming more interesting. It's something I've spent a lot of time on, but I don't really have a chance to talk about it now. I think that the killer applications for private 4G and 5G are either where you have moving IoT, so that's things like vehicles and robots, or indeed people walking around with, say, a two-way radio. I think that particular use case of voice is a really interesting one, particularly where you have organizations that don't use traditional cell phones, but have various sorts of two-way radio and walkie-talkie. And that is going to start transitioning to smarter devices that are capable of doing push to video, new classes of messaging, as well as acting as mission critical terminals. And I also think that, as I've discussed before, the OT industrial operational technology side is certainly going to become more important for both the cellular and the Wi-Fi sides of this. So, just before I hand over to Vladan, how do I conclude all this? The first one is, it's very tempting always to talk about convergence, but frankly, probably for the last 20 years, I've actually also talked about divergence. And what we tend to find is convergence on certain layers of technology stack, and then a divergence in applications or delivery mechanisms. And in this case, we're seeing a steady rise in the number of ways in which companies can get their wireless connectivity on premise, whether that's with new classes of spectrum, new classes of service provider, perhaps services that are coming from their other vendors, their cloud vendors, their IoT vendors, their industrial automation vendors. And I think that's important to recognize, as well as the convergence message, and that there will be points of intersection between Wi-Fi and public and private cellular, but in some cases the speed and cadence of development will mean that they're actually run independently. Wi-Fi will retain a core role for a lot of use cases, and I think there's an awful lot of misapprehension at the moment that somehow 5G is going to replace Wi-Fi. It isn't. They might compete for some new use cases, but in other cases, one or the other will make complete sense, and there will be almost no overlap. I think the demand side from IoT and also public safety, which I haven't really touched on in how you do good indoor public safety networks, that presents particular new challenges for 5G given the frequency bands, and also some other aspects such as the massive MIMO antennas. We're seeing new stakeholders and service providers emerge. And then in terms of what happens and what's changed compared to if I'd done this presentation 3 or 4 months ago, the pandemic, I think we'll see a short-term slowdown in indoor 5G, partly because of supply chain, partly because of a lack of access to certain premises and travel for engineers. I think that should change in a 6 to 12 month view. I think we're certainly seeing more focus on work from home Wi-Fi than in-office Wi-Fi for obvious reasons, though I suspect that in future we may well see those converge and get combined as an overall connectivity strategy for on-premise employees and working from home. There's a lot going on behind the scenes to prepare, especially around 6 gigahertz, I'd say. Longer term, we like to see more interest in certain verticals that we might have thought about a year ago. Obviously, government, healthcare, utility, logistics will do better at the we should expect than, say, airports or retail or leisure venues. Although hopefully on a 2 to 3 year view, those sectors should rebound as well. I think we'll see what I'll call smart buildings and pandemic-proof buildings, which have the wireless network inbuilt capability to do, say, occupancy sensing, enable social distancing, and so on. And the other question, which I'm not going to have time to touch on today, is what the impact of geopolitics is. We're all aware of what's going on at the moment, and certainly on the cellular side, this move towards Open RAN rather than perhaps single box small cells, and what the impact that has on private and in-building networks is still a little bit unclear. So that's how to get in touch with me. I'm Disruptive Dean on Twitter, and I'm now going to hand over to Vladan to do his presentation.
Thank you very much, Dean. If you can handle the commands, please.
Yeah. Should have that now.
Very good. Okay, so hello everybody. My name is Vladan Jevremovic. I will be talking about private 5G networks, and here is my agenda. And here is also a very cute puppy, because I was told that in this era you need to spice up your presentation. So I present to you my my private bodyguard, my dog. So iBwave presentation. Industrial plant 5G requirements. I'm going to talk about a little bit about one of the use cases for 5G, and this one is going to have a lot of things that you have not seen before in private 5G networks. We will get to it in a moment. I'll talk about industrial plant indoor network design challenges, and I will talk about industrial plant indoor network design best practices, and I aim to do all this in less than 20 minutes, including a demo that I will present, which will show an example of a design of industrial plant indoor network, 5G indoor network. So let's get started. What are the industrial plant 5G requirements? Basically, what we have is ultra low latency for the reason of plant robotics control and augmented reality AR demands. They require ultra low latency because if you don't have it, then industrial accidents may happen. If you cannot get a hold and control your robot fast enough, then that is a recipe for disaster. You cannot tolerate large delays of your signal. The same goes true with augmented reality. So in 5G, a latency is the function, among other things, of transmitting time interval, or TTI. And in 5G, it is scalable. Up until 5G, that was fixed. In 4G and LTE, it was 1 millisecond. Here, it can go anywhere from 0.125 to milliseconds to 2 milliseconds. But not all of those 5 options are available in all bands. As you are aware of, there are 2 distinct frequency bands in 5G. One is sub 6 gigahertz, and then there is a millimeter wave. And in general, millimeter wave has a shorter TTI, 0.25 and 0.125. So you see right away that the millimeter wave may be more appealing for the purpose of running augmented reality application and robotics control in industrial plants. So from the design standpoint of view, the best option is what we call numerology number 3, which is option number 4 in this particular slide. There we have a feature of both data support and synchronization support. So all of them can change every 0.25 milliseconds. And the spacing subcarrier, which is another characterization of 5G, is 120 kilohertz. Now that is a feature of 5G. The larger the subcarrier spacing, the shorter the TTI. So it stands to a reason that for large subcarrier spacing, we have a very, very short TTI. Now, let's move on to industrial plant indoor design challenges. Number one, there are lots of metal objects in an industrial plant. And those are assembly line robots, industrial machines. The question is, how do you model them? How do you model them in RF design and planning software? Then the next challenge is that a floor plan may change over time. Now, how is that possible? Well, say you have a car factory and that particular plant is producing a particular make and model of a car, the particular make of a car. Now, over the years, a company may decide to discontinue that particular make and start, with a new make and model. So that would require that those assembly plants can be redrawn and rearranged. And so that may not seem like much, by the time when you are putting your wireless system in there. But, maybe in 5 or 10 years, maybe there is a different floor plan layout, and maybe you will need to, if you do not plan for a change, maybe you will need to go and add additional antennas. Then there is lots of movable objects. What it means is that movable objects may partially or completely block your signal for a period of time. And those robotic arms, they move in real time. Also, the network downtime is not acceptable at all. You have to provide with signal path redundancy. What it means is that if your small cell goes bad and if it starts transmitting, you have to have a second path to your sensor or some other receiver that would allow for a connection even if one or more antennas are down or small cells are down. And then finally, this was one last requirement is not the same in all regions. Specifically, there are regions like in Japan where the regulatory body says, well, you have to do a very good containment of your indoor network coverage. If you have a private, or as they call local 5G network, we will give you frequency to build a private or local 5G network in your factory, but you have to contain your signal. You cannot really let the signal creep outside. So that is rather region or country specific, but it does exist, those requirements. So now, what are the best practices based on what I just said? First of all, don't place transmitters near metal objects. I have given you some extreme examples here when antenna panel is hanging, from what looks like metal objects, and we see another antenna that is being hidden behind a wire mesh. And people will tell you don't do that, but they don't explain why. Well, here is the thing. If you place your antenna in a near field of your if you place antenna in a near field of a metal, or in other words, if you place metal near the near field of an antenna, what's going to happen is your antenna pattern is going to change. It will not be what is in the spec sheet, it will be something else. And that something else, may prove to be either too much for your system to handle or just create too much interference. Basically, your signal will show up in a place where it's not supposed to show up and will not show up in a place where it's supposed to show up. So don't do this. The next one is place your transmitters in a warehouse along corridors. In millimeter wave, and this is where we want to design our 5G network at, a signal cannot propagate through boxes and containers. And that's why you have to put your transmitter at the beginning of an aisle and maybe at an end of an aisle as well. Don't try to put your antenna pattern to be perpendicular to the boxes. Just let it go along the corridor. The next one is to provide a redundant line of sight signal. As I said earlier, you do not have a luxury to be able to afford downtime. So what happens if the forklift stops in front of your transmitter? It will break your signal if you are in millimeter wave. Millimeter wave signals do not propagate well through objects, through solid objects like walls or cardboard boxes and what have you. So you have to have a second line of sight, a second antenna that is able to reach your transmitter. And in this case, we say that we provide for a redundant signal. Sometimes you can use large fixed metallic objects to your advantage. I told you that the signal doesn't propagate well through materials, with a few exceptions, but it does reflect very well from metal. So in millimeter wave, you can use a fixed metal object as a reflector for your millimeter wave signal to reach your sensor if the sensor is screened off behind another large object. So this shows an example, how to do that. And finally, as I said, indoor signals should stay indoors, and that is country specific. But if that is your requirement, then you have to be careful not to point your antenna in the direction of a glass window if you have a directional antenna, or if you have omni antenna, don't put it near glass window at all. So if you do have directional antennas, don't point at the window, but point inside the area. So that would limit your signal leakage very well, because the outer walls in a factory are usually of concrete walls, and they do not let millimeter wave signals out at all. Now, finally, I'm going to talk a bit for the last 10 minutes or so about this case study of a design of millimeter wave 5G network in industrial plant. So I am going to use a synchronization signal to plan coverage, and I'm going to use numerology number 3 to achieve ultra low latency. So I have SCS of subcarrier spacing is 120 kilohertz. That corresponds to numerology 3. My output power over 100 megahertz band will be 20 dBm, and my RF channel frequency reuse be 4:1, meaning I have a total of 400 megahertz spectrum at 28 gigahertz, and I'm going to use 4 100 megahertz channels, and those are non-overlapping channels. My target design for synchronization signal RSRP will be minus 96 dBm. So the question is, why minus 96 dBm? Why not minus 100 or minus 80? Well, let's go back to what we know. We know LTE and we know LTE channels. So for a 10 megahertz LTE channel, I know that my target RSRP should be minus 95 dBm. That's what we have seen in our industry for the last 10 years or so. We know that we have 600 subcarriers at 10 megahertz LTE. Okay, so what do we have at 100 megahertz 5G channel? We have a little bit more. We have 792 subcarriers. When I take 10 logarithm of the ratio of the two number of subcarriers, I see a 1.2 dB difference. That means that I have to add 1.2, well, in this case, subtract 1.2 dB to get the equivalent level of RSRP signal for SS in 5G. And when I do that, I get neg 96.2, which is approximately neg 96. Okay, so now I know what I want to do. I want to provide coverage over area in industrial plant when machinery is operating. That is my goal. So now I have to go and switch my screen to demo. And this is a 2D presentation of my industrial plant factory. So those areas that you see that are a little bit darker are the areas where you actually have metal machinery. And what you have above it are 5G multi-beam antennas. I'm going to go quickly and show you what those antennas look like. So this is your pattern. Those are multi-beam antennas. And they are operating at the 28 gigahertz. And from the specs here, we can see that the gain is 9.95 dBd, a little bit over 12 dBi. Right? So going back to the industrial plant, my goal is to point them down towards these areas with metal machines, and I have to also somehow model the losses that those machines have. So I'm going to go to 3D plant to give you an idea how it looks like. So what you are seeing here is the areas where the machines are. This area here has a little bit of a reddish hue. I called heavy machinery area, and you can see that those are pictures of how that may look like. This area here is what I called light machinery area, and they are, modeled a little bit differently. So what I have done here, I have actually placed antennas above, and I'm going to give you a little bit of a better angle to see where they are. Okay, so there is one of them. As you see, it is pointing straight down. That antenna is about 4 meters above the floor, whereas this heavy machinery, light machinery area is about 2.5 meters above the floor. You will see that also that I have placed them toward the edge of the area pointing down. So whenever I could, I would place them over the edge of an area, but I also have antennas that are pointing down, that are in the middle. So you see there is one over here and one in the corner and one over there. So again, my goal is to have neg 96 dBMSS RSRP. And what I am going to show you now is how I achieved the coverage. Oh, by the way, the penetration loss is different for those, the heavy machinery area and light machinery area. We will get to that in a second. But first, I'm going to say that I am, for the first analysis, I'm assuming that my RSRP is going to be recorded at the level, at the top of the machinery. Okay, and as I said, this is supposed to be neg 96 dBm, so I am now showing you in my legend 2 colors. RSRP less than neg 96 is red, and the one that is less than neg 96 is blue. So everything that is red is a good coverage. And so if I want to show you how it compares with the area where the heavy machinery is. I'm just going to move the horizontal, the surfaces above, and you see those, that's the area where the heavy machinery is. So that area is red, meaning that RSRP is very good. So I have achieved my goal, assuming that all the sensors are located on top of heavy and light machinery. Now the second one is if I put my sensors that are not on the top of the machine area, but a little bit below. Remind you, the machinery area is 2.5 meters tall. And in this example, I put sensors at 2.5 meters. I'm going to put sensors at 2 meters, which means now they're going a little bit deeper inside the area where the machines are. When I do that, the coverage is all of a sudden not so good. The coverage has shrunk, right? So just to make sure that you understand how it is, I'm going to move the horizontal surface above the prediction. You see those within rectangles. I have a lot of blue. So that really means that having your millimeter wave signal go through the area with the penetration losses is going to hamper your coverage quite a bit. So you don't have a good coverage if your sensors go about half meter deep into your machinery area. So this is just an illustration. What are the issues that you may yourself finding out there? Now, similar situation is if you look into MADR. MADR is a maximum achievable data rate, and there at I'm going to move this surfaces down and just move a little bit to the left, so you will see how it look like in this area here, where it is very clear. And mind you, this is 4:1 frequency reuse, right? So there you see that I have a coverage, I have a MADR of about 270 megabits per second. Those are 100 megahertz channels. 270 doesn't seem like much, but this is TDD, right? So, and this is a balanced uplink downlink. So you basically, the total throughput for uplink and downlink would be twice this. Would be about 575.80. So if your sensor is above the machinery clutter, you see how you have nice coverage there as far as maximum achievable data rate. When you drop it down within the clutter, then what's going to happen again? It is going to drop significantly, right? So for example, here the upper one shows you at 2.5, it was almost 270, and then it went down to 201 if you dropped it into the clutter. Here, it is about the same, but here there is a definite delta, and so on and so forth. So that's what I wanted to show you. Keep in mind that this all is done with the 4:1 frequency reuse. We had a 100 megahertz channel. Of the total of 400 megahertz channel, we needed to use quite a few antennas to achieve this coverage. To give you a sense how big this is, this is about 130 meters across, and I think it's about 170 or 180 all the way down. So this is quite a big, factory. It is not humongous, but it is not small by any means. If you want me, I can tell you in feet. This is about 400 feet across. So this concludes my my presentation for a demo. I will now go and finish this off to present you again the same puppy, but with the summer cut, and open this to Q&A.
Thank you very much, Vladan and Dean, for your great presentations. That's a very cute dog. We won't have that much time for questions. I suggest we take 2 of them. And maybe what I'm going to do is I'm going to publish a blog post with all the unanswered questions, because we received some very interesting ones. So maybe the first question I have for you, Dean, this is the question. So I've seen a lot of discussion on this topic, but in practice, no one seems to be moving forward. Has the technology not reached the point of widespread acceptance? Is this a case that the IoT devices aren't evolved enough, or is there no first mover advantage?
Right. I think it depends on what you're referring to. There's quite a growing amount of private 4G around, where the devices are often actually just either phones or ruggedized handhelds. I think that for the type of IoT implementation that you heard from Vladan just now, there are modules that are around. Now, they are mostly for 5G non-standalone. Which is not the fully private network, but ones which will be driven by a service provider predominantly. So I think that you'll see this sort of cut over the next year as standalone chipsets become available and standalone core networks where you have full private 5G. But I think until then, we'd have quite a lot of private LTE that's being deployed in Europe, North America, Japan, and elsewhere, albeit for probably more standard mobile broadband use cases rather than the ultra reliable type of thing we're hearing here.
All right. Thank you, Dean. Vlad, a question for you. For the use of private 5G networks with the use of privately owned spectrum, how much spectrum would typical services of the different enterprises need? And what spectrum bands will the private networks operate on? And what bands would be preferred for privately owned spectrum?
Well, yeah, so that is a loaded question. We have a CBRS spectrum, Dean has mentioned. CBRS spectrum is a 3GPP spectrum. So it can be 4G, it can be 5G. Now, when you go down below 6 gigahertz, you have limitations as to how big your RF channels would be. And, so the question is, how much spectrum do you want to bid on for CBRS? How much spectrum would be given as a tertiary or secondary user or general public use? And those are multiple 10 megahertz channels. So grab as much as you can for your enterprise needs. If you are looking for what I have just shown you, which was industrial case network, then you may need to look into things such as latency and maybe your requirements for video. And if you have requirements for video, you will need quite a bit of spectrum, right? So your limitations really are like this. In a high band, when there is a lot of spectrum, your limitation is realistically 100 megahertz per RF channel. You can have multiple RF channels, but 100 megahertz per RF channel is your realistic limit because of the limited power that your phone has. Remember, everything that all the power that your phone is transmitting is going to be spread over the RF channel given. It is not realistic to have 400 megahertz RF channel to be transmitting on a phone at once. 100 megahertz is about the top limit. That is on millimeter wave. Down in the lower frequencies, I would imagine that you will not be given that RF channels will be much less wide, much narrower. 20 megahertz, I imagine, would be limit for one RF channel. But to answer your question directly, it really depends on what your regulatory laws are and also what kind of applications you want to run.
All right, makes sense. So I think we're going to conclude now. So again, I will put up a blog post in the next days with all the unanswered questions. And I would like to thank you very much, Dean and Vladan, for your insights. Again, you really offered us some great content. So thank you. And thank you to our attendees for joining us on today's webinar. We hope you
Thank you.
enjoyed it. And
Thank
I
you
wish you a very pleasant afternoon and rest of the week.
Thank you very much, Clarice. Thank you very much,
Thank
Dean.
you.
Thanks,
Goodbye.
Vladan, Clarice. Bye.